those integrated rate laws. Remember that each of them have a specific sort of concentration time equation. Each of them have a specific half-life equation, which obviously is the time it takes for half of whatever you started with to basically go away. In addition, they all have very specific sort of graphs that represent them. So for example, first order is the natural log of the concentration on the y, and I guess spit that out right. Natural log of concentration versus time, and that yields you a straight line. The other one there is 1 over a, which gives you on the y for the second order, which goes in the positive direction. Then we have just the concentration versus time, which is our zero order, which has that negative graph associated with it. So each of those, again, are specific for those types of reactions. In addition, you can identify the type of reaction you're dealing with by looking at the rate constant, and more specifically, the units associated with the rate constant. By seeing a certain type of units, you'll know that you're dealing with, say, a first order reaction versus, say, a second order or a zero order. Again, first order typically has reciprocal seconds, or some type of 1 over unit of time. Second order has 1 over molar seconds, and usually zero order there has molarity over seconds. So again, like we talked about, they won't always in like really blinking lights go, hey, we're dealing with a first order reaction here. They will sometimes just give you the rate constant and the units, and you can use that to determine sort of what you're dealing with. We then talked about towards the end there, sort of the effect of temperature on reaction rates. As we increase the temperature, again, everybody's gaining a little bit more energy and enough energy to get up and over that activation energy. So remember that E of A is that minimum amount of energy for a reaction to occur. It's really, as we saw, sort of the hill that the reactants has to climb to get to the other side. And by increasing the temperature, we get a greater fraction of molecules that have enough energy really to get up and over that hill to the other side, to the product side, as we can see in this last graph here that we left off with, which is basically a comparison of two different temperatures. And we see that the red graph there, which is the second temperature, which is a higher temperature than the first, where we hit the activation energy, we have a much larger area of molecules that have enough energy to kind of get up and over. So by increasing the energy, it allows everybody to sort of react quicker. It also allows them to have enough energy for that reaction to take place. Remember that just a collision alone between two things doesn't necessarily guarantee that you will get a reaction formed, or I guess a products formed. You do need to sort of hit everybody in the right orientation. You also need to hit it with the right amount of energy to sort of kick off that reaction. So remember that just because we do get a collision doesn't necessarily mean that we will get products that are formed in a particular case. We saw sort of the Arrhenius equation, and one version of the Arrhenius equation, which basically relates kind of temperature to the rate and also activation energy as well. We saw sort of the graphing version of it. And again, the graphing version of it looks like, I believe we should have that on the next page, I think, is this guy right here. And that is basically written in the form of y is equal to mx plus b. And when we do this sort of graphing version of this equation, we basically graph on the y, the natural log of k. On the x, we would graph 1 over the temperature. This is in Kelvin. And basically when we would do that, we will yield a actual slope, or a line that has a negative slope. When we do that graph, we'll end up with something like this. And the slope of that line, as we can see here, is equal to that term right there, which is minus E of A over R. R is a gas constant, is the gas constant, and it is the one that involves energy. So not the one that we use for gases. It's the 8.314 version of the gas constant. Again, this line here is going to be negative in terms of the slope, and the negative here, as we talked about, will typically turn our activation energy into a positive number. And again, that makes sense if you think about those curves that we saw. You know, this is the activation energy here, and basically got put in energy, right, to get up and over that hill. So it's usually a positive number when you do that. You also should, when we talk about it sort of mathematically as well, or keep in mind unit-wise, sometimes we do run into some situations between these two things. Usually in terms of units, activation energy is given in kilojoules, and in terms of R, obviously one of the units are joules. So at some point when we sort of mathematically use this to solve, we will perhaps run into some issues. You got to do some type of conversion sometimes. And again, you can either convert it joules to kilojoules or kilojoules to joules in that particular case. Any questions on any of that stuff that we were talking about last time? Okay, so let's take a look at sort of a problem where you would use sort of a graphing technique, if you will, to basically solve it. So if you were given sort of this data, our table here with all this information, we want to determine the activation energy from this reaction. So what we would do is essentially we would want to make our plot. And again, our plot is going to be the natural log of K on the Y, 1 over the temperature in Kelvin on the X. And what that means is if you were given this table, pretty much for your temperature column here, you would need to go through and take 1 over the T because it's already in Kelvin on both of these guys. And for our K, you would then need to go through and take the natural log of K for each of those. And then those would represent points that you would obviously plot on this graph. You would do your best fit line, very badly drawn there, and obviously you would get your equation from it. Probably wouldn't want to do this by hand, probably would want to lay up maybe an Excel graph or something like that, but you know, that's sort of the method that you would do. So they did that for us, which is really nice. And we do end up with basically this equation that y equals minus 1.12 times 10 to the 4x plus 26.8. So we could use the equation from this line to figure out what it wants, like the activation energy and the frequency factor. And we could do that by really using the slope value there. So for example, if we wanted to figure out the activation energy. The activation energy can be found by looking at the slope because the slope equals minus E of A over R. So in this particular case, our slope there was 1 point. So basically the E of A would equal minus the slope times R if we rearrange it, multiplying the R to the other side and the negative as well. And putting that in there gives us negative, and again, our slope was negative 1.12 times 10 to the 4. And we do have our R, joules per Kelvin per mole. And if we do all that, again, that negative slope and that negative sign there is going to turn this into a positive number. And it looks like we do end up with 1.12 to the 4th times 8.314. Gets us something like 9.31 times 10 to the 4 joules per mole. And again, we get that from really the graph information or the graphical information there. Any question on that calculation? Now, the other thing we wanted was the frequency factor. Frequency factor is A. And if you remember in that equation that we talked about there, it is the natural log of K is equal to minus E of A over R, 1 over T, plus the natural log of A. And again, this is Y is equal to mx plus B, which means if we are interested in our frequency factor, we basically want the y-intercept to use, and that's what B stands for. But remember that that does not equal A. That equals the natural log of A is equal to the y-intercept. And that means that the natural log of A would equal, in this case, our y-intercept of 26.8, I believe it was. And because it was 26.8 there, we're going to get rid of the natural log by taking the E of both sides. So we would take the E of this guy and the E of that guy there on our calculator. The E on this side and that will cancel out and basically leave us A. And if we take the E of that 26.8, that's going to give us 4.36 times 10 to the 11. And the units here would actually be 1 over molar seconds, as basically when we come back here, we're basically doing the y-intercept, which would be up in this range. Y-intercept is the natural log of K. And when we take the E, or the inverse of the natural log goes away and these units come back. So they end up being the same units as the rate constant because of that, because we have the natural log. And in our math we just did, we essentially took off the natural log, and that's how we get back to kind of the same units that are associated there with the K value. Any questions on that there?
Professor, could we go back to the example one just to get, yeah, thank you. Just, I didn't copy down all of the second.
Yeah, no worries.
Thank you.
Other questions on this? So this is sort of a graphical approach to sort of determining things like obviously activation energy, frequency factor, things of that nature. Now, we don't usually use graphing a lot of cases, but this is obviously what you would do if you really were given just a kind of table like we were in this problem of K and temperature. The other thing is important, again, just like in most chemistry, right? Sometimes temperature is given in degrees Celsius. So you do want to make sure that obviously is converted to Kelvin here when you kind of do the graph. Again, probably some type of graphical program like Excel or something like that would be a good way of doing this. Now, obviously, we don't want to always sort of do graphing, and we don't have to necessarily do graphing in all situations. We can actually do sort of a mathematical version of this as long as we have kind of like 2 points basically along that line. So if we have information about kind of 2 points along that line, we can actually just kind of solve it more mathematically than sort of graphically. And to show you that equation, it's a kind of a similar looking equation. And you will, if you maybe look around and stuff, we'll see a few different versions of this equation. So we'll go with this one here. But sometimes they distribute the negative out, and sometimes they combine the denominator and stuff like that. So there's maybe like 3 different versions of this equation out, but we'll stick with this one here. That's the natural log of K2 over K1. Those are obviously 2 rate constant values, equals E of A, which again is our activation energy, over R, which is the same gas constant. So again, that's going to be our 8.314 version here for R, just like we just used. And 1 over T1, again, needs to be in Kelvin. That obviously is the temperature for the first rate constant. 1 over T2 would be the temperature for the second rate constant. And this one here, since it is mathematical sort of solving of this, this is the one where, again, people do run into that issue of units. Usually this is in kilojoules when it's given to you. Again, obviously, as you just mentioned, that is in joules. So again, it doesn't really matter sort of which way you choose, but you got to do some type of conversion when it's all said and done. So either take the joules to the kilojoules or the kilojoules to the joules. But you do need to do that conversion. Otherwise, you're going to be off, obviously, by a factor there of 1,000. So let's take a look at an example here. Give you a chance to do it. Why don't you give this a go? The reaction for this has a rate constant 2.57 at 701 and 567 at 895 Kelvin. What is the activation energy? So take a couple minutes here and see what you come up with. Okay, let's take a look here and see how we're doing. So in this case, again, we could use sort of the mathematical version of that equation that we talked about. Again, because we have 2 points pretty much given to us. We have, and again, you can label these however you want. Usually people just kind of go in order. So we'd call that K1 is 2.57. Our temperature one would then go 701 with that. Our K2 would be 567, and our T2 would be 895 in this case. Using our natural log of K2 over K1 is equal to E of A over R, 1 over T1 minus 1 over T2. In terms of units, we're okay here. The temperatures are already in Kelvin, so that's all good. So basically just need to kind of plug everything in. So that's going to be the natural log of our K2, which was 567 divided by 2.57. That's going to equal our E of A, which is what we're trying to find, divided by our value there. Again, 1 over our temperature, so it's going to be 1 over 701 minus 1 over 895. So doing some cleaning up here of the math, we would take something like 567 divided by 2.57 and then take the natural log of it. So that would give us something like 5.3964 equals E of A over 8.314. I'm going to kind of clean up what's inside the parentheses there. So 1 divided by 701 minus 1 divided by 895. That gives us something like 0.000309215. That means I need to multiply that to the other side. I need to divide that to the other side afterwards. And if I do all that math there, I'm going to end up with a number. Let me see, where's that number? There it is. That times 8.314, we're then going to divide it by what's in the parentheses. And that's going to end up giving us a activation energy of 145096. These would be in joules at that point. Again, joules based off of this guy right here. At this point, usually would go to kilojoules. So divided by 1,000 gets us about 145 kilojoules for our activation energy. Question on that calculation, where any of the numbers came from or anything like that. Again, we see that our activation energy is a positive number here, which again is what we would expect it to be actually in this particular case. Any questions on that example? Okay, so let's take a look at another one here and see what you come up with. All right, so why don't you give this one a go? So as we talked about earlier, in practice, if you sort of raise the temperature by 10 degrees Celsius, you expect a doubling in the rate. So calculate the activation energy, and here they give you some hints. So take a few minutes here and see what you come up with. Okay, so let's take a look. So in this case, they don't give us some rate constant sort of numbers, but they talk about the rate basically doubling, which basically means that, from our first temperature here to our rate constant in our second temperature, we're going to see basically a doubling of it, which essentially means we got pretty much the natural log of 2 there happening on this side. It's going to basically end up as 2. Again, because as we put that in there and we substitute that in, that's basically the K2 equals 2 times K1. When we do that, we get 2K1 over K1. And again, those guys cancel. We end up with 2 because, again, we essentially doubled it. Equals our E of A over R. And again, the temperatures that they chose, which again was a 10-degree separation between the two. 300 Kelvin was our T1, and 310 Kelvin there was our T2. Sort of the same sort of situation here in terms of the math. We're going to take the natural log of 2 on the left. That's going to be 0.693 times 8.314 to bring that to the other side. Going to get us 5.762825 equals E of A. Again, if we clean up what's inside the parentheses there, we end up with 0.000107527. That again is going to be divided now to the other side. That's going to give us our E, and that would be something like 53594 units. Again, are going to be joules based off of this guy. Again, Kelvin's going to cancel. It's really joules per mole, as the moles in it cancel. And again, since it is usually kilojoules, we'll just kind of move that 3 places over, and we end up with perhaps something like 53.6 kilojoules per mole, which is our activation energy in this particular case. Any questions on that calculation there? So this is was sometimes referred to as sort of the 2-point version of the Arrhenius equation, sort of the non-graphing version. You basically just need, as you can see here, 2 points. In these couple of examples, we solve for activation energy, but you obviously could solve for a rate constant. You could solve for obviously a temperature as well, depending on the information given to you. So you won't always be solving for activation energy, but it is a common sort of thing that you do solve for. But you could solve for like a rate constant, could figure out like a initial final temperature type situation. So has to rearrange all these guys here sometimes. Any questions on temperature and the Arrhenius equation or anything like that? Again, so one is more of a graphical version where, you know, we use the graph in the equation to help us solve for things. This obviously is sort of the non-graphical version of it, where again, to do this, you pretty much just need information about 2 points really along that line, essentially. Any questions on this equation here? Okay, so the last thing we're going to talk about in this chapter then is, you know, how reactions sort of come together and what's sometimes referred to as reaction mechanisms. So reaction mechanisms, as we'll talk about, is sort of a plausible explanation for how perhaps a reaction does take place. Just a reminder, as we talked about, I think earlier as well, you know, not all collisions will lead to products being formed. So in the top one there, again, the K and the CH3I do sort of intersect each other and collide with each other sort of in the right orientation, and we do see products being formed. But, you know, if this guy sort of backed in with the carbon side first, we would not necessarily see any products formed. So again, there are those 2 factors that are important for products being formed, as we talked about, not only the collision, but you do have to collide in sort of the right location, and you also have to obviously collide with the right amount of energy. So when we do get some of these collisions and these sort of reactions to occur, one thing that you're probably familiar with is the idea that not all reactions basically occur in like a one-step type situation. So what's meant by that is, you know, when we make something like A plus B makes E plus F, we sometimes think about these reactions as, oh yeah, it's just like a one-step type process that occurs. And that's not necessarily always the case. We could have, for example, a reaction where A plus B makes C plus D. then C plus D react to make E plus F in sort of a step 1, step 2 type process. If we were to add these together, things on opposite sides of the arrow will cancel out or reduce. So if there's a C on the left, a C on the right, they cancel. D on the left, D on the right, they cancel. And that leaves us with this reaction that we saw above. So sometimes when we look at it, we think it all happens at once, but what we see here is it actually is sort of a multi-step process that occurs. You probably saw this in Chem 51 when you dealt with everybody's favorite thing, Hess's law, where you add up all those individual reactions to sort of make a overall reaction. So it's sort of the same idea here. So when we sort of think about reactions and how they occur, we think about reactions as sometimes these mechanisms which involve sort of individual steps, which are these simple little reactions that occur. But when you add them all together, you get sort of the overall reaction that occurs. And these sort of simple elementary steps are sort of steps along the way, are what are referred to as elementary steps. So elementary steps are these kind of individual reactions that when you add them together, sort of paints the whole picture and kind of gets you to the overall reaction that you are sort of looking for. So for example, when we do this reaction here, when we take some NO and some O2, we make some NO2 in this particular reaction. But when this reaction is taking place, N2O2 is actually detected. And obviously, when you look at this reaction, there is no N2O2 that is present. So what that would imply is that this reaction as written doesn't necessarily occur in like a one-step process. Obviously, because this guy is detected, it had to be made somewhere along the way and then get used up. So this had to be made, then get used up. And to sort of explain this or possibly explain what's going on, we can basically look at this reaction as these elementary steps here, where the first step, for example, is a couple of NOs come together to make some N2O2, which is why perhaps we have seen that be detected in this process. But then very quickly, perhaps in the next step, that N2O2 gets used up to make our NO2, which is our product. Again, if we add up each of these elementary steps, we could cancel out whatever is the same on opposite sides of the arrow. In this case, it would be that N2O2, as was referred to sometimes as an intermediate. That's something that is sort of made early on in the mechanism, but gets completely used up. And we are left with our overall reaction that is happening here. So mechanisms try to sort of explain or describe a possible path by which a reaction can occur through these sort of individual elementary steps. Any questions on that there? And again, here, just sort of visually see what happens. We make that N2O2, then that N2O2 gets consumed along the way, not present in the overall reaction, but obviously detected along the way, which means obviously something was made. And that is basically the definition of an intermediate. An intermediate is really something that is made in a reaction mechanism sort of early on in an earlier step. But the important part in order to recognize something as a intermediate is that it gets used up by the end of the reaction. And what that means is that the intermediate will not appear in the overall reaction. So that's an important distinction. In this case, the N2O2 kind of over circled there. So it's actually just this guy. The N2O2 on both sides there will get canceled out because it is an intermediate. And what that leaves us is everything on the left-hand side of the arrow, we have two NOs. And again, that O2 shouldn't be circled. I've got the O2 and then our two NO2 on this side. Now, when we look at sort of elementary steps, we can think about them in a couple different ways, and they're sometimes referred to as the molecularity of a reaction, and that's basically the number of molecules that are reacting in an elementary step. So unimolecular is basically an elementary step where you have just one reactant, like a decomposition type thing. Bimolecular is where we have a couple of reactants basically coming together. And termolecular means we have one with up to sort of 3 molecules reacting. This guy here would be bimolecular, right? We got 2 guys reacting. And same thing down here. We have the N2O2 and the O2 reacting, which would be bimolecular in each of those cases. Now, one important thing when we look at sort of mechanisms and rate laws is we could actually, for each elementary step, we could write a rate law. And we could write a rate law a little bit different than how we normally get to the rate law. And that is when we're dealing with elementary steps and we're dealing with reaction mechanisms. If you remember, when we do write the rate law, we do not use the coefficient as the exponent, but this is the only place where that is acceptable to do. So in these elementary steps, you could actually use the coefficients that are there to write a completed rate law for that particular step. And again, that is the only place sort of in kinetics where it's acceptable to use the coefficients in the equation as the exponents. So if we had a unimolecular elementary step, this would be the rate is equal to K times the concentration of A. And again, it is 1 because the coefficient here is technically 1. If we had a bimolecular, it would be the rate is equal to K times A times B. Again, both of these are essentially 1, which is why both of these are essentially 1 in this case. This right here is A plus A, which is a fancy way of saying 2A, right? Goes to our products. And again here, because the coefficient is 2, that is why we put the 2 here. So different than what we were talking about pretty much for the rest of this chapter earlier on as well. This is, again, the only place where it is acceptable to use those coefficients as exponents in their rate laws when you're doing mechanism, and specifically when you're writing those rate laws for an elementary step. So how do you determine if, like, I'm looking at this mechanism, I got all these sort of individual reactions given to me. How do I know this is perhaps a good mechanism or a bad mechanism? So there's really sort of a couple of major things that you want to look at when you're trying to determine, hey, is this a good mechanism or is this a bad mechanism? The first one is pretty simple. You know, you have an overall reaction you're looking for, and that means that when you add up all the elementary steps, all those individual sort of equations that were given to you, it needs to add up to the reaction that you're looking for. So if you add up all these reactions and it doesn't match the reaction you're looking for, not a great mechanism, it's a bad mechanism. If you add up all the individual steps along the way and they do add up to the overall reaction you're dealing with, then so far, so good. Doesn't necessarily mean it's a good mechanism, but so far, so good. So that's one very important thing. Obviously, when you add up all the steps, they need to equal the reaction you're looking for. The second one is that when you determine what is referred to as the rate determining step, and that is sometimes referred to as the RDS, the rate determining step, it needs to match the rate law that was found experimentally. So a couple types of problems or mechanism problems that you're given. One very common type is they will tell you that in the laboratory or in an experiment, it was observed that the rate law was whatever it is. So they'll kind of give you the observed rate law. And through either calculations or looking at the mechanism, you need to find the rate determining step and the rate law that goes with that guy. And those two guys should match. And if they do match, then that again means this is a good mechanism. If they really don't match, then that means it's a bad mechanism. So how do you know what step is the rate determining step, or what is the rate determining step? Let's first talk about that. The rate determining step is pretty much the slowest step in a mechanism. And since it is the slowest step in a mechanism, that means that you're pretty much waiting for that step to happen in order for the entire reaction sort of to complete. So it's like when you go shopping and you go to the 15 items or less line, and the guy's got like 300 items in front of you. That is your rate determining step, right? You got to wait for that person to sort of pass through the line until you can get through. And that's sort of the same idea here. In the mechanism, there will be something that will be sort of the slowest step. Now, how can you determine that? Well, there's a couple of ways. If they give you sort of the experimentally found rate law, and you can write a rate law for a particular step that matches, then that's probably your rate determining step. So that's one sort of problem where they really don't give you information other than the observed rate law. You should find one that matches a step, and when you do, that would be your rate determining step, the rate law that from the step that matches the one found experimentally. The other way that they typically will do it is they will have a reaction like this, and next to it they'll write fast, and next to perhaps the next step they would write not step, but they would write slow. And it is the one labeled slow that is the rate determining step. So that's another very common way in sort of mechanism problems that you're able to determine sort of which one is the rate determining step. So if they're nice enough in the mechanism to sort of label those steps for you, you could definitely determine the rate determining step by the one that is recorded here as the slowest. If they don't sort of label the steps for you, then what you're going to find through sort of your calculation with the mechanism is you will find a step that will have a rate law that matches the observed or experimental rate law exactly, and then you'll know that is the rate determining step. Any questions on that? Okay, so let's take a
Could you repeat?
yeah.
Oh, I'm so sorry. Could you repeat the last part so that it matches what again for the rate law?
Yeah, so there's a couple of different types of mechanism type problems. So there's one where they won't sort of label each step, and they won't say, hey, this is the fast step or this is the slow step. So in those situations, what they will tell you though is that the rate law for the experimentally found rate law is something. So they'll give you sort of the experimentally found rate law. And what you'll find in those type of problems where they don't really label each of the steps as fast or slow or something like that is you could go to each of the steps, and at some point you will find a rate law for a particular step, say the second step in the mechanism, and you write the rate law for the second step. That rate law that you wrote for the second step will match the one that's experimentally found. And because they match each other, that means that that should be your rate determining step. So in a problem where they really don't give you that information, like, hey, in blinking lights, this is the slow step, this is your slow step, this is your rate determining step. In those type of problems where they don't do that, you will be able to match a rate law for a particular step to the one that's found experimentally, and that will tell you that that is your rate determining step. Other questions on that? You're welcome. Okay, so let's take a look at one here. Again, here are some of the steps to follow measuring the rate of a reaction and formulating a rate law, and then postulating what sort of happens there. So why don't we take a look here at one and kind of discuss what's going on here. So why don't you take a second and see what you come up with for these answers. So experimentally, the rate law was found to be K times NO2 squared. What is the overall reaction we get from this mechanism of these two steps? What is the intermediate? And what do you think about the rate of the first step versus the second step? So why don't you take a couple minutes and we'll talk about it and make sure hopefully everybody's on kind of the same page. Approach this. So first off, what we want to do is figure out the overall reaction. So obviously the overall reaction is found essentially by just pretty much adding everybody together. So we just want to add everybody together here and cancel out whatever cancels out. Again, you can think about sort of the arrow as like an equal sign, so kind of subtracting off from the other side. So if we were to add these guys together, we would see NO3 would cancel. We would also see NO2 would cancel. And that leaves us on the left-hand side here, NO2 plus CO goes to NO plus CO2 there if I added everybody together. Any questions on that part of it? Now, when we're looking for the intermediate in this particular case, the intermediate is, in this case, NO3. Now, what about NO2? Is that an intermediate? And hopefully you determine that it is not an intermediate. So although it does reduce down, like we see here on the left and right-hand side, it is still present in the overall reaction. And the definition of an intermediate is something that gets made early on, but gets completely used up by the time the reaction's over. And what that means is it should not appear in the overall reaction. So since NO2 does appear in the overall reaction, that means that this NO2 is not an intermediate, even though we reduced it down. And the only intermediate here would be our NO3. Any questions on that one there? All right. So when we look at each of these individual steps along the way here, we can write a rate law for each of them. The rate law, again, and this is the only place where we could do this, we can use the coefficients as those exponents. So the rate for the first step would be K times NO2, and it would be squared. Again, basically, these two guys is 2NO2. We could write a rate law for the second step where the rate would equal K times NO3 and CO. And in this particular sort of mechanism here, they didn't label any of these as fast or slow. So this is what I was talking about earlier, that they didn't really label it for us, which one's fast or slow. So we can use these rate laws and the one that they gave us from the experimentally found one to help us determine sort of what is happening in each of these steps. So what we see is the one that is determined experimentally, the experimentally found rate law is the rate is equal to K NO2 squared, which means what we know is the rate determining step should have a rate law that matches that identically, and that would be NO2 squared. And when we look at each of the steps, we do see that step number 1 has that exact same rate law. So what that means is step number 1 is the rate determining step or the slow step in this mechanism. Step 2 should be a faster step. So really step 1 is really the part of the mechanism in this particular situation that's really determining sort of how fast this overall reaction will take place. Once it kind of gets past that first step, we know that it probably will proceed at a pretty good rate at that point. Any questions on that? So this again would be a type of mechanism problem where they didn't explicitly straight up front go, hey, number 1 is the slow step, right? But we were able to determine that the first step was the slow step by finding the rate law for the first step and seeing that it actually did match perfectly the one that was found experimentally. Clearly, when we look at number 2, his rate law, it does not match at all to the one found experimentally. So we definitely know that number 2 is not a slow step or a rate determining step. Any questions on that?
Professor, yeah, I'm a little bit confused on that last part, just like determining um, experimentally and what that means. Got a little lost there.
Yeah, so what that means is, or what happens is, a lot of times in these rate law problems, they will give you this rate law here. And this rate law here is sort of like the experimentally found rate law. So it's really sort of the rate law for the overall reaction that's happening. It was somebody did an experiment essentially and determined, hey, for this particular sort of reaction, this is the rate law that's happening. What really determines sort of, how fast a reaction sort of proceeds is really sort of the slowest part of this mechanism, right? So the slowest part of this mechanism is the one that really determines the overall rate of the reaction. So when they determine sort of experimentally what the rate law is, they're saying that this is really what is determining how fast this reaction is happening. So when we look at a mechanism like we see on the screen with these two steps, we can find a rate law that has, or a step that has a rate law that matches it exactly. And in this case, that was step number one. And what that essentially is telling us is that step number one has the same rate law that was found experimentally. And that means that step number one has to be really the slowest step in the mechanism. It's the one that's really sort of determining how fast this reaction is going to happen. It's kind of like the wall
Okay,
that, you kind of has
so
to pass through to get to the other side.
I see. So because they match, that means it is the slower one.
Right. And it is what is referred to as the
Okay,
rate determining step. Yes. And if we look
got
at
it,
step
got
number, yeah, we look at step number two, it clearly the rate law for just step number two doesn't look anywhere near the one that was found experimentally,
it.
which means
Right.
it's really not the one that's determining how fast this reaction truly is happening, because
I
slow step is really the one that determines, are you going to sit there for like 30 seconds, or are you going to sit there really for like an hour, for this reaction sort of to take place. And that's why we're looking for a step that matches it in this type of problem, to know that that is this rate determining step.
Okay, that makes a lot more sense. Thank you so much.
You're welcome. Other questions on that? Okay, so again, this is one type of sort of mechanism problem where, as I mentioned, that's sort of the case. They don't sort of in like blinking lights sort of tell you, hey, this is the slow step. This is going to be your rate determining step. Um, so let's take a look at one where they sort of do kind of tell you that. And let's take a look. Actually, we'll come. We'll come back to this. No, we'll do this one now, actually. Let's take a look at this one here. So this one here, we have several steps happening here. And we have basically a three-step mechanism. This is the overall reaction that we're looking for. And this is the experimentally found rate law, or the observed rate law, sometimes referred to. So what we see here in the first step, this is a reversible reaction. So this is basically arrows heading in both directions. And this one is labeled fast. Then we have this second step, which is slow. And we have this third step, which is fast. So for each of these things, we can actually write a rate law for. And what we're trying to do here is really determine, is this a kind of good mechanism? Is kind of what we're looking for. Is this a possible way that this reaction basically can proceed? So the first thing definitely we want to do, right, to determine is it a good mechanism is, do we get the overall reaction when we add up all the steps? So that would be kind of the first thing that you would want to look at. So basically you would add up all these steps and you should hopefully end up with this reaction. So let's take a look if that is the case. So we want to look for things on opposite sides of the arrow that cancel. So I see N2O cancels. Let's see, anything else that cancels? I have N2O2 on the right, N2O2 on the left. So those guys cancel. And I think that's it in terms of canceling. So we're going to take everybody on the left and keep it on the left. So we have two H2s. We have two NOs, so that's good so far. On the right-hand side, we have two waters there, so that's good. And we have an N2. So we see here that once we get rid of our intermediates, we are left with a reaction that does match the overall reaction we're looking for. So far, that is good in terms of this being a good mechanism. Any questions so far on that? Now, the other thing that we need to do to make sure that this is a good mechanism is we need to determine which one is the rate determining step in this case. And what should happen is the rate determining step should have a rate law that matches the one that was found experimentally. Before we do that, let's also talk about a couple of things that I just erased, but there are some intermediates here, right? And the intermediate that we crossed out was N2O. Again, does not appear in the overall reaction. We also had an intermediate that was N2O2, which also does not appear in the overall reaction, right? So in this particular case, they did label each of the steps, and this is probably the easiest one to figure out which one is the rate determining step. It would be this guy, because he is labeled really the slow step. So in this mechanism, step number 2 here would be the rate determining step, which means when we write the rate law for this guy, it should have a rate law that matches the one that was found experimentally if this is a good mechanism. So, excuse me, let us write the rate law for step number 2. So for step number 2, if we write the rate law, just like we've done before, the rate would equal K times our reactants, which in this case would be H2, and it would be N2O2. Now, when we look at this rate law and we want to compare it to the one that was found experimentally, if you look at it right as it is at this moment, you may say it does not match. And you may be right, or you may be wrong. And the reason you can't really compare the rate law as it is here to the one found experimentally is when we look at the rate law for step number 2, we have this guy that's in it. And this guy is a intermediate. So it's kind of like comparing apples to oranges. You got to be able to compare sort of apples to apples. So what this is going to require you to do in these type of problems is you need to get rid of the intermediate and kind of substitute it out. So how do you get rid of that intermediate to substitute it out? Well, you go look at some of the other steps along the way to help you. So in this particular case, the only other step that has N2O2 in it is step number 1. It's the only step that has it. Step number 3, no N2O2 to be found. Now, step number 1 is a reversible reaction where we have 2NO goes to N2O2, and then it comes back the other way, and they label it like this. Now, because this is a reversible reaction, it will eventually reach equilibrium. And what that means is the rate of the forward reaction will equal the rate of the reverse reaction. So eventually this reversible reaction will reach equilibrium, which means the rate of the forward direction, which is going from reactants to products, will equal the rate of the reverse direction, which is going from products to reactants. So in this reversible type reaction, we actually can write not one rate law, but we could actually write 2 rate laws, one for the forward direction and one for the reverse direction. So for step number 1, for the forward direction, the rate law would be the rate is equal to K times NO squared. Again, kind of going in that direction. If we wrote a rate law for the reverse direction, going in this direction, we could write that the rate is equal to K times N2O2. Any questions on how I got those two rate laws there? One is for the forward direction and one is for the reverse direction. Okay, so how is this sort of going to help us get to where we need to be? If you remember, what we are looking for is something to substitute into here, which means we need to solve for N2O2. Now, as I mentioned before, at some point, this reversible reaction will reach equilibrium, which means although I do not know what this number is, the rate, what I do know is they will equal each other. And because they equal each other, what that allows you to do is basically set those two rate laws that you just wrote equal to each other. So we could say that K times NO squared is equal to K times N2O2. And again, that is because these two rates should equal each other. That again, hopefully you can see is helping us because we really want to get to N2O2. So to do that, we're going to divide K to both sides. And that would get us that the concentration of N2O2 would equal K times NO squared divided by K. If you want to be really specific here, this was K1 and this is K minus 1. And what that now can do, or what we can do with that, get rid of that part, is take that whole thing and basically substitute it into our rate law for the second step again, because now we have really what N2O2 equals. Any questions onto that move there? Now, if we do all that and kind of clean up everything, let's see what we end up with. So substituting that in, we end up with the rate is equal to K times H2. And again, substituting in our guy there, K1 NO squared divided by K to the minus 1. Now, we could actually do some cleaning up here. The K here, the K here, and the K here. Those are all rate constants, which means a rate constant is a constant number, which means although we don't know what it is, we do know that at least one of them on top and one on the bottom will cancel each other out. And now if we clean up what we are left with, we have the rate is equal to H2 times NO squared. And now we have a rate law that does not have an intermediate in it. And now we can compare it to the one that was found experimentally. And if you look at it at this point, you might have thought earlier, it's no way it matches. But what we see now is this guy and the one that was found experimentally actually do match because we got rid of that intermediate that was there, so we could compare apples to apples. And because the rate laws match, that is good as well. That means that this is a good mechanism, a possible mechanism, a plausible mechanism for how this reaction would take place. So this is another type of mechanism problem where you kind of has to, it's kind of like in math, right? Proofs, like you know the answer, but you got to prove it. So you have to do some substituting using all the steps to get to a place where you get rid of the intermediate in a rate law. And that way you could compare the two to see if it does match. In this case, again, they both match, which means it's a possibly good mechanism. Doesn't mean this is always how this reaction occurs. No. But it's a plausible sort of explanation as to how this reaction could occur. If you did this whole sort of substituting in and everything like that, and you got to the end like we did, and it did not match the rate laws, then it would mean it's a bad mechanism. Question on that particular one there. All right, so now that I did one, why don't you do one here and see what you come up with. Based on this mechanism here, again, the first one is a reversible reaction. Is this a good mechanism? Is this a possibly plausible mechanism for this one? The observed rate law, or the experimentally found rate law, is up there on top. The rate is equal to K times O3 squared and O2 to the minus 1. So take a couple minutes and see if you think it's kind of good or bad here. And you do have to kind of prove it. So see what you come up with, and we'll talk about it. Looks like O here on both sides will cancel, and I think that is it. That's going to give us 203 on the left and 302 on the right. So far, not bad. That matches. Remember that the rate law found experimentally here needs to match the rate law for the RDS. And in this case, they did label these guys for us. So because that's the slow step there, that should be the rate determining step. That means, like we talked about previously, the rate law for step number 2 in this case should match the rate law that's found experimentally. So let us write the rate law here for step number 2. So for step number 2, the rate law would equal K times O3 times O. Again, just a reactance involved, just like normal. Again, we cannot really compare this rate law found experimentally to this guy because, again, unfortunately, our rate law here contains an intermediate, right? That's the intermediate we sort of canceled out. So we again need to do some substituting to sort of get rid of that intermediate and allow us to get, again, a rate law that basically represents everything sort of in the final reaction and not really an intermediate. Again, because step 1 is a reversible reaction, we can write 2 different rate laws for it. Again, for the forward direction, the rate law would be the rate is equal to K1 times O3. For the reverse direction, heading in that way, the rate would equal K times O2 times O. Just like we talked about before, when this guy reaches equilibrium, the rate of the forward direction will equal the rate of the reverse direction, which again means we could set both of these guys equal to each other. And that means that K1 times O3 is equal to K times O2 and O. Again, we are looking to substitute in for O here. So that's what we want to solve for. So to do that, we're going to divide this to the other side. Those guys will cancel, and that will give us that the concentration of O is equal to K1 O3 and K minus 1 O2. And again, minus 1 is what that should have been there. Minus 1. At this point, we now have something that we can take and substitute in for our intermediate. And if we do all that good stuff there, that will get us the rate is equal to K times O3. Now, substituting in what we have there, we have K1 O3 divided by K to the minus 1 O2. Again, the K on top and K on the bottom will cancel. And now if we clean this up a little bit, we end up with K O3 squared divided by O2. And now we have a rate law that we can compare to the one experimentally. And when you do, you hopefully see that they actually do match, because that is O2 to the minus 1, which is basically 1 over O2. And that's why the O2 is on the bottom here. So it matches actually in this particular case. You could again write this as K O3 squared and O2 to the minus 1. So because the rate law matches the one found experimentally, and because the overall reaction adds up, That means that this is pretty much a good mechanism. It's a possible mechanism of how this occurs. Any questions on that step there? Okay, so this is again pretty much a mechanism type problem, obviously, and a little bit more complicated one where you have to do some math, some substituting. But again, the goal here is to get really two rate laws that are sort of apples to apples to each other and compare them and see if they match. And again, if they do not match, then it's probably not a good mechanism. Any questions on that?
I have a question.
Yeah.
So in this example, there was a negative exponent in the rate law. Is that normally seen in like other rate laws?
It's possible. It is possible for it to occur, as you can see here. It occurs because really we end up with kind of O3 squared divided by O2. So it is possible, actually. Yeah.
Would it be possible for reactions outside of like the rate mechanisms?
Um, I I don't think too often you would probably see it, to be honest with you, but in sort of mechanism type situations you can. But maybe like if you're asking kind of like ones we did previously,
Yeah.
you probably wouldn't see too much of it. But it can obviously happen here in these type of sort of situations. And again, that's because these mechanisms are, they're not 100% exactly how these reactions perhaps occurs every time, but they're sort of possible explanations or pathways that a reaction could take. So I would say in like problems we did previously, probably more whole numbers is ones that you get and probably not so much negative exponents, but they do sometimes pop up here in sort of mechanism problems.
Okay, thank you.
You're welcome. Other questions? Okay, so we'll wrap it up there. We're pretty much done with experiment 12, and we're done with experiment 12. We're done with chapter 12 almost. We have a couple more things to talk about, so obviously we'll do that on Thursday. I think it's probably a good idea to take a quiz, so we'll take a quiz next Tuesday on chapter 12, so everything kinetics, and we'll do it probably at the start of lab on Tuesday. So we'll take the first little bit of lab and we'll do a quiz, and I'll let you know how we'll do it on Thursday, if we'll do it through Zoom or we'll do it through Proctorial. So I'll let you know